Prove the statements in 1 through 11. In each case, use only the definitions of the terms and the assumptions listed on page 161, not any previously established properties of the odd and even integers. Follow the directions given in the section for writing proofs of universal statements. If a and b are any odd integers, then a squared plus b squared is even. Now here are the assumptions from page 161. We always start our proof by writing proof and underlining. Now this statement form is a conditional. This is an implication. This is an if-then statement. One of the best ways of approaching a proof for this statement is to start by assuming the premises of this implication. So we'll start by saying assume a and b are odd integers. Now I want you to notice something about the quantification here. The way a and b are introduced in this statement is that a and b are arbitrary and fixed, whereas the statement is a universally quantified statement about any odd integers, any pair of odd integers. We're not taking every pair of odd integers here. We're just assuming a and b are specific, fixed, arbitrary, odd integers. But we're going to show that this property holds that a squared plus b squared is even, regardless of what a and b are. The next thing we can do is we can unpack what it means to be an odd integer. By definition of odd integers, a equals 2k plus 1 for some integer k. Similarly, b equals 2n plus 1 for some integer n. Now you might be wondering why I used n here instead of k. That's because a and b are supposed to be arbitrary and fixed odd integers. We never assumed that a and b are the same odd integers. This integer k is introduced as a fixed variable. And so if we say that a equals 2k plus 1 and b equals 2k plus 1, would mean that b and a are the same integers. But that's not necessarily the case from our assumptions. That does not follow from the previous statements. And so it's important to use a different letter here so that we respect the locality of these variables. Okay, so now we've unpacked the definition of an odd integer. Now I think it's understandable if a student might get confused at this point. We've taken our assumptions, we've unpacked our assumptions, but we haven't led to any conclusions yet. The conclusion, though, is supposed to be that a squared plus b squared is even. So that means after a few statements here, we should have the conclusion that, therefore, a squared plus b squared is even. We have to figure out what goes in these lines here. We have to somehow bridge this gap using logic. Instead of working from your assumptions, we can work backwards from our conclusion. What does it mean that a squared plus b squared is even? Well, that means that a squared plus b squared equals 2m for some integer m. Okay, so now that we've worked backwards from our conclusion, we have a clearer picture as to where we need to go. We need to show that a squared plus b squared equals 2 times some integer, and that's by definition of odd. Okay, so now we have to somehow bridge the gap here. We want to show that a squared plus b squared equals 2 times some integer. So let's investigate what is a squared plus b squared. Well, according to this list of assumptions at the top here, we may assume the principle of substitution. So we can substitute 2k plus 1 and 2n plus 1 into a and b respectively. So a squared plus b squared equals 2k plus 1 squared plus 2n plus 1 squared. And this is by substitution. Now we're going to want to do some algebra with this new expression that we have. So by algebra, 2k plus 1 squared plus 2n plus 1 squared, we could start by expanding these expressions by multiplying the factors. This is 4k squared plus 4k plus 1 plus 4n squared plus 4n plus 1. Next, we want to somehow factor out a 2. So we could say this is 2 times 2k squared plus 2k plus 2n squared plus 2n plus 1. So next we need to check whether or not this thing is an integer or not. This expression is ideally what we want m to be, and we need to ensure that m is an integer. So let's clarify why this thing is an integer. Well, we can assume that the set of all integers is closed under addition, subtraction, and multiplication. So next we could say, let m be this integer. Next, we can clarify why this is an integer. Since the integers are closed under multiplication and addition, we could say that m is an integer. And that's the final proof. Now we've officially bridged the gap between the assumption and the conclusion. And if you notice, it's important to be able to work in both directions, from the assumption to the conclusion, and working backwards from the conclusion towards the assumption. That way, the missing logical connection that you need to make is as small as possible. Thanks, everyone, and I'll see you in the next video.